Good afternoon, everyone. My name is Adam South, and I work for Kennametal in our Innovation Ventures group. In that group, I focus on developing new technologies and business models that are further away from Kennametal's core competency. While we wait for PowerPoint to reload here, I'll just tell you the agenda for the day, for this presentation. I'm going to start out reviewing the challenges that are facing Kennametal both today and tomorrow. Then we'll discuss the difference between this new approach to improving productivity that we're taking in our own facilities, compare the current approach to this new approach. I'll explain how the system works, and then we'll close things off with the benefits and the lessons learned. First, just to give you an overview of Kennametal, in short, we deliver productivity to our customers in demanding environments through materials, processes, and or finishing products and services. Those may be delivered in the form of a wear-resistant coating for food processing equipment, or it could be metal cutting tools used in the aerospace or transportation industry. We are a global company with global customers, including ourselves. So Kennametal is unique in that we use our own products in our own plants every day. We manufacture our cutting tools with our own cutting tools. So while we use the same products, we also have a lot of the same needs as our customers. And you see 6 of these listed on this slide. And what I want to go through next is talk through the needs or the challenges that are facing Kennametal both today and tomorrow. Here we see a simplified version of a part production process. And the challenge that's really facing Kennametal today is how do we decrease the time to go from art to part, where we start with a solid model or a CAD model, that's the art, and we step through a number of selection, planning, and programming functions before the final product is actually produced. Now, this process isn't entirely accurate because oftentimes what happens is this is an iterative process. When the part hits the shop floor, problems are often identified that requires a user to go back to an earlier step in the process and make edits or rework or changes. This oftentimes results in lead times as long as several weeks. Our strategy, our objective is we want to decrease this lead time down to hours by leveraging digital assets and analytics. And what I'm going to speak about for the rest of the presentation is one specific technology that demonstrates the potential of the industrial Internet of Things. But first, let's take a look at tomorrow's challenge. Now, this says tomorrow's challenge, but in reality, this is already hitting Kennametal today. It's just that these challenges will continue to get worse in the near term. And the first one here is that manufacturing. So this isn't just Kennametal. This is a lot of manufacturing is facing talent erosion. If you go into any manufacturing facility, especially here in the U.S., you're going to find a very high proportion of workers that are very skilled, very experienced, very knowledgeable, but are also rapidly approaching retirement. And when they retire, with them goes their knowledge and their experience. What you can lay on top of that then is the increasing complexity of machinery and tools. Machines continue to have more axes, more spindles, more complexity. And from the cutting tool side, Kennametal doesn't make it much easier. If we were to stack Kennametal's catalogs on the table here, we'd have a stack of catalogs about 10 or 12 inches tall and about 100,000 products for a customer to try to navigate. And that's just one cutting tool manufacturer. Then consider the new talent generation. As these older workers are retiring, the younger generation is entering manufacturing in smaller and smaller numbers. Those that are entering this complex environment are coming in with new service expectations. So they don't have the experience or the knowledge, but they expect all of that information to be available at their fingertips. And the last one, of course, is the productivity imperative, the continued need to produce more with less resources. These four megatrends, along with the need to decrease the time to go from art to part, is what led Kennametal to partner with System Insights, our partner company of which Will Sobel will be on the panel in a moment, to partner with System Insights to develop a new approach to improving productivity that targets each of these megatrends. I want to start the explanation of this new approach with our objective, and that was to maximize productivity in our own machine shops. When I say productivity, what I mean is we're focusing on improving throughput, where we're measuring throughput by increased producing hours and decreased cycle times. And now what I want to explain or touch on here is the correlation between these two metrics and throughput. What we have on the chart on the right of the slide here is periodic data. We can say that this is monthly data, showing the number of pieces that a plant produces and the number of hours that were required to produce those pieces. As you can expect, there would be variation, and that variation can differ whether you're a high-mix, low-volume facility or a low-mix, high-volume facility. But the important takeaway is that there is a fit. In this case, it's a linear regression showing us that, as expected, the more time that a machine is producing, the more pieces it will produce. And that's the premise on which the current approach is built today. But in order to increase that producing time, we have to decrease our downtimes. And in order to decrease downtimes, we have to know the cause of the downtimes. So the current approach today is to leverage real-world machine data to improve productivity by identifying, classifying, and quantifying downtimes to feed into process improvement projects. Visually, it looks like this. When you decrease your downtimes, your producing times are going to increase. That, of course, increases your throughput. So you can think about the current approach as moving users up along this throughput producing hour regression. Also keep in mind that this approach is optimizing your downtimes. It's not touching producing times. It's only looking at the periods that your machine is down. This new approach tackles the problem from a different direction, where we start to optimize the producing periods. It is built on the premise that decreasing cycle times will increase capacity for additional throughput. Cycle times are decreased when tools are applied at more productive cutting conditions. And as we said with one of the first bullets in the megatrends, experienced operators possess knowledge regarding past productivity gains. And I'll show you an example of one of these findings when we move on to the benefits section. And so this approach measures and quantifies how tools actually perform on our shop floor and recommends best practices across a user community, whether that's a single facility or multiple facilities across Kennametal's organization. And it looks like this. When we apply tools at the more productive cutting conditions, cycle times decrease. And you can notice here that as cycle times decrease, your producing hours actually go down because we're increasing capacity. That capacity can be filled with additional parts to increase throughput. So while the current approach moves users up along their throughput regression, the new approach actually changes the slope of that line, where now you actually produce more pieces per unit time. This slide compares the current state and the future state of what you'll find in most manufacturing facilities today. The blue lines are showing the flow of information or communication. The dotted lines show how this typically works today, and the solid lines show the communication gap that we close with this new approach. So I'm going to start in the upper left-hand corner at the programmer, where a programmer programs a part based on his or her knowledge and experience of the part to be produced, the machine, the tools, and the processes that will be used. That part is then posted to the machine, and so to the machine go things like the part program, setup sheets, or work instructions, and then the part is produced. At that point, any number of things can occur. Maybe there's a tool breakage, maybe poor surface finish is realized. In other cases, there are productivity gains where the operators run these tools at conditions more productively than what the programmer initially intended. But that's where the communication often stops. That experience, that knowledge does not make its way back to the programming functions. What we've done is we're collecting real-world data from these machine tools to understand the actual speeds, feeds, and cycle times of every tool and part that's going through our shop floor. We also provide a UI for operators to provide feedback on what worked well and what didn't work well. This is then analyzed in the cloud, and what comes back to the programmers are recommendations. These are best practices or improvement opportunities where the system identified parts that are about to be produced can have their cycle times reduced by implementing what your best operators are already doing on the shop floor. This slide shows how the whole system works, and I'm going to start in the upper right-hand corner here at the user facility. We collect two types of data, metadata, which I'll come back to, and machine data, or MT-Connect data. MT-Connect is just the standard that we're using to collect this data. So as you can imagine, a shop is full of many different machine tool makes and models that all provide data, proprietary data. MT-Connect basically translates this data. It gives it meaning so that cross-device analysis can be performed. This machine data, or MT-Connect data, is then collected by a data aggregator, which is nothing more than a PC or a server that exists on that user's network and is connected to the internet. And it transmits this raw performance data, the speeds and feeds at which the tools are running, to the cloud. But as you can imagine, the machines only provide so much data on the actual process. So they're not going to provide information on the workpiece material, the hardness, the actual individual components that make up a cutting tool assembly. That's where the metadata comes in. And we've worked with a number of third parties to collect this type of data from CAM packages, from tool management systems. We now have enough data for a comprehensive analysis, and we collect the same types of data from other users in the community. Rules and analytics are applied, and what's coming back then to the user facility are knowledge-based recommendations. These recommendations are based exclusively off of real-world data. So these users are receiving optimized cutting conditions that will decrease cycle times. They're also receiving notifications of optimized tool selections, all with the objective of improving throughput. On this slide, we have four different benefits that Kennametal has realized in our facilities, and we'll take a look at all four of them in detail. But just from a high level here, first I'll talk about how we see this tool being used to improve our planning accuracy, how we've used this system to learn from our most experienced operators and also improve our less experienced operators. And then the last example will showcase how this type of data can be used to identify best practices between two different facilities. This first case is from a part that was produced in one of our plants, and what we're looking at here is cycle time data. So the bars are showing us the cycle time of each individual tool or process step. The lines are showing the cumulative time that it took to produce this part. And you'll notice from the key here that we have planned and actual data. When this part actually ran on the shop floor, it ran exactly according to plan. Operators made no edits or overrides to the program. But if you notice, this part took about 30% longer to run than what we had initially planned. And what you can see is if you look at process steps 2, 3, and 5, you notice that the actual cycle times are significantly higher than the planned cycle times. And when we dug into this further, we found that there were actually some inaccuracies coming out of our simulation packages on specific types of operations, complex operations that were impacting our process planning. The next example shows how we can learn from our more experienced operators. And what we're looking at here is, this is data for a tool inside the plant. We call it MC96. I'm only pointing that out because we'll I'll reference this same tool in the next case. The x-axis of this chart is showing feed rate, which is correlated with metal removal rate or cycle time. As your feed rates go up, so does your metal removal rate, and your cycle times go down. The y-axis is showing how many observations we collected from each instance of this tool. And what you can see from this chart is this tool was always programmed to run at about 800 millimeters per minute. You can also see that most operators are running below plan, but the more important finding is this more experienced operator that's running this tool at about 25% greater than plan. This was the kind of knowledge that we wanted to capture with this system and distribute across all of our operators in our facilities. And this next example shows the results of doing so. What we see here in this table are 3 tools on the left side that were used to produce a part. The actual column is what a less experienced operator was actually running before this system was providing recommendations. Notice that in every case, this operator was running that tool below plan. By collecting this data and finding the best practices in the facility, we then recommended back to this operator to run where the best operators were already running. And you see those conditions listed in the optimized column. The end result was that both sets of conditions were producing quality parts, but in the far right column you can see that by implementing the best practices, we were reducing cycle times per tool between 20 and about 40%. The last example, the last case is an example of what we call the enterprise community. This is where we analyze how in this case, the same part was manufactured in 2 different facilities. And what we're looking at here is, again, we see the blue bars are showing us the time in cut that was required for each tool that was used to produce this part, and the orange line is showing us the cumulative time that it took to produce this part. What we found was that plant 1 was about 15% faster than plant 2, even though if you look across the bottom of the chart, you can see that plant 1 uses 1 extra tool than plant 2. I don't have the chart here, but when we found this, we looked a level deeper into the speeds and feeds and how this was actually being produced. And what we found was plant 1 was using a high-speed machining approach, where they were running the tools much faster, but at very light depths of cut. Whereas plant 2 was running the tools much slower, but at very heavy depths of cut. The takeaway here is that plant 2 can't just blindly implement the approach of plant 1. Maybe there's another limitation. Maybe the machine isn't capable of high-speed machining. But what's more critical here is we now have the data to back this up and determine whether or not this 15% reduction in cycle time is enough to justify standardizing on machines. I wanted to wrap things up with some lessons learned, and what lessons learned wouldn't be complete without an acronym, and this was a data science project, so we have our data sci acronym here. The first is dedicate a resource to own the system and the improvements. This software is no different than any other software you use, whether it's Office, a CAM software, ERP software. They all require a user. All this system will do is provide recommendations. It will not improve anything on its own. So you need a user that can dig into the data, can investigate the recommendations, and determine the next steps and actions in the plant. The next is act on the data, information, and knowledge. The first thing most people hear whenever a project like this is kicked off, and we heard it as well in our plants, is this is Big Brother looking over my shoulder. The quickest way to get past that is to act on the data. So when we implemented this in our shops, we told our operators that it was mandatory to classify downtimes and deviations from plan. What was optional was the free-form entry of any comments. And what happened once we started acting on their data and improving the processes was we saw an uptick in these comments, these optional comments. So we realized that we were starting to get some buy-in, and we found some very valuable findings, feedback from the operators that were identifying issues with the machine tool or issues with a specific cutting tool that we weren't previously aware of. When we acted on this, you saw more and more buy-in, and very quickly the perception changed from this being Big Brother to we're all working together here to try to improve our productivity. In calendar year 2014 alone, we had over 5,000 free-form comments from just one plant. The other way to get buy-in is through transparency. Your operators really don't need access to all of the reports and recommendations, but they should, if they don't have access, they should at the very least be kept informed of what's being measured and how it's being used. This helps with buy-in as well. Next, we have the approach. So while this isn't Big Brother, it certainly could be used as Big Brother. It could be used to identify your worst performing employees, your workers, but that would really be missing the point. The better approach is to reward or incentivize your best workers, encourage everyone to do the best and implement the best practices that have already been used across your shop floor. Next is standardize to scale, and this also really fits with integrate with other systems. As I said earlier, the machines can only provide so much data. It's really not enough for a comprehensive analysis. So when you can integrate with other systems, whether it's ERP, CAM, tool management, the amount of value you generate drastically increases. Standardizing on those systems is also a tremendous value, because now when you go from one plant to the next and you're using the same systems, you don't have to start over again from zero and learn how to do this, how to implement this all over again. And the last is cloud comfort is required. So this system does require going to the cloud because this is a big data analytics solution, and it's just not economically feasible to try to deploy this on-premise and perform the big data analytics. So there needs to be comfort with transmitting your data up to the cloud for this type of an analysis. That's all I had. I'm out of time, so I think we'll be answering any questions during the panel. Thank you.